You can describe the image created by a concave or convex mirror qualitatively using a ray diagram. Using the relationships that you observe from that ray diagram, we can form some quantitative or formulaic relationships. Before we can derive the equations that define the relationships of the images created by these mirrors, we need to understand the variables at play, starting with the distance of the object, d sub o, or dou. This is how far the object or that initial arrow is from the center of the mirror. Then there's d sub I, the distance of the image. Likewise, this is how far the image is located from the center of the mirror. A positive d sub I tells us we have a real image. It's in front of the mirror on the same side as the object. A negative d sub I tells us it's behind the mirror. It's a virtual image. The generally inverse relationship between di and dou is based on the focal length, which is half the center of curvature of the mirror. Now, for a concave mirror, it's a positive focal length. It's in front of the mirror. It's on the same side as the object. For convex, those mirrors that diverge or spread out the light, it's a negative focal point. The focal point is behind the mirror. This convex ray diagram shows us that the object is on the opposite side from the focal point in a convex mirror. We can also look at the variables of height. H sub O is the height of the object. This is how tall that initial arrow where the light is starting from, how tall it is. Relative, we have the height of the image, which is how tall that blue arrow is on the opposite side in this case, because it's virtual. Now the height of the image tells us something. If it's upright, it's a positive H sub I, which makes sense. It's on top. If it's inverted, we're looking at a negative H sub I. Curved mirrors can create both virtual and real images that are either smaller or larger than the original object. Magnification is the ratio between the object's original size and the size of the image that's created. We can use a concave mirror's ray diagram and our old friend trigonometry to explore this relationship. With the right formula, we can calculate the magnification or predict the individual heights or distances of the object or created images. To derive the magnification formula, we need to start with a ray diagram. Straight focal, focal straight, and where the reflected rays cross, we get an image. Now, if I look beyond those two sets of rays, I go from the tip of the object to the tip of the image. I prove that theta I equals theta R. Those angles are equal. That means I have two right triangles, each with an equal angle. These are similar. So that means when I apply trig, tangent theta equals opposite over adjacent, my opposite and my adjacent make it negative because it's inverted HI. Opposite, adjacent, they're similar, so those are equal. Using a little bit of our cross multiplication shortcut, we can reorganize things. We already saw that the distance of the image could possibly be positive or negative depending on the image, so I'm going to move that negative over there. After we reorganize the formula, we get the magnification formula. M, magnification, which is the multiplier for how much bigger or smaller an object is compared to its image, is equal to both HI, which is the height of the image, divided by HO, the height of the image, or it's also equal to negative DI, which is the distance of the image, divided by DO, the distance of the object. This formula can be used a couple different ways. HI divided by HO equals DI divided by DO, or you can use either of those ratios to calculate the magnification. You may remember this equation from the 1938 classic Snow White and the Seven Dwarfs.
Hi-ho!
Dido. Dido.
For example, a concave mirror is needed to produce an image that is 1/4 or 25% the size of the object. What is the image's height if the object is 16 meters tall? We know the magnification is 1/4 or 0.25, 25%. The height of the object is 16 meters. We want to know the height of the image. So we know that here's our formula. There's our magnification formula. We're looking at HO, HI, and M. So I'm just going to use that first portion. Plug in what we know, and then we solve for what we don't. HI divided by 16, so I want to solve, multiply both sides by 16, which means 16 divided by 4 is 4 meters. The image, in this case, would be 4 meters tall. The focal length of a concave mirror defines how it converges light. The focal length of a convex mirror is located behind the mirror, causing light to diverge or spread out. The placement of this focal length changes the position and size of the image created. We can solidify this relationship into a formula. With this formula, you'll be able to predict or calculate the distance of the image using the focal length of the mirror. The Mir formula takes the focal point into account. We need to start with another ray diagram. Straight focal, focal straight, there's our image. Now I'm only going to look at one of those pairs. I see 2 right triangles. I know that those 2 angles that are touching each other are equal to each other. So I have similar triangles again, same idea. So I can find my opposite and my adjacent. Now it's not the distance to the object because the distance of the object minus the focal point. Then my other one, that's the height of the image, and that's the distance to that focal point or the focal length. Same idea, those relationships are equal because I have similar triangles. We can use our shortcut to switch things around. Bring the HI down, bring the DO minus F up top. HO divided by HI, we already know, is equal to the opposite DO divided by DI. So I can switch that out of my equation. Now I can start breaking that fraction apart. DO divided by F minus F minus, or divided by F, that's really going to be 1 when I divide those out. If you divide both sides by DO, you end up with 1 over di equals 1 over F minus 1 divided by DO. And then I'm going to simplify that all into what we call the Mir formula. 1 over di, the distance of the image, plus 1 over DO, the distance of the object, equals 1 over F, the focal length. Another way to say this is the inverse of the distance of the image plus the inverse of DO, the distance of the object, equals the inverse of the focal length. 1 divided by is the same as saying inverse or reciprocal. Let's give it a try. An object located 12 meters from a concave mirror creates an image 8.6 meters from the mirror. What is the mirror's focal length? List out your givens, because if you list out the givens, the formula writes itself. There's only one formula that has those 3 variables. Substitute in what you know. Now, instead of trying to type out tricky fractions, take a moment to use your calculator. We're going to type in 8.6 inverse plus 12 inverse. That'll give us 0.2. Now, that's not the focal point, so I need to take the inverse of 0.2 to get a focal point of 5 meters. Just like remembering to take the square root of a complex formula, remembering to take the inverse of this formula is a very common error. Let's try a convex mirror problem. An object is placed 4 meters from a convex mirror with a focal point of 7 meters. We'll always double check this. I know a focal point for a convex mirror should be -7 behind the mirror. Now, if I'm creating this mirror, I should be able to predict where the image is located. I know the distance the object is located. I know the focal point is -7, and I'm trying to find the distance of the image. There's my formula. If I write out my givens, the formula writes itself. Substitute in what you know, solve for what you don't. Now, here's a big tip. Align all those fractions, all those inverses together. I'm going to subtract 1/4 because now I can go to my calculator. -7 inverse minus 4 inverse. That's going to equal -0.393 if I round a bit. And then I remember to take the inverse of that. So my final answer is about -2.5 meters.